In last video, we have derived expression for an integral f(x) times gx. So gx is a linear function. So gx equal to mx plus n. And we have derived so this integral is equal to gx bar and times a. So if we see this in coordinate systems, we can see. So if this is a xy coordinate systems. So we have fx. So fx, if we say fx is a curve like this, and so this is point A, this is point B, and gx, we know gx is a linear function. So we say gx is like this. So from this expression we know. So if we do an integral from a to b, fx gx. So the A is the area. It's the area of fx from A to B. So area under fx from A to B. And the x bar is the x coordinate of the centroid point of the area A. So what is that? So for this area, if we see here is the centroid point of this area, we see this centroid point is C. So the centroid point have a so the coordinates of this centroid point is x bar, y bar. So this is x bar. So this is the x coordinates. So once we know the x bar, so gx bar is the gx at the magnitude of gx at x equal to x bar. So this is gx bar. So A is the area and fx from A to B. And gx bar is the magnitude of gx at x bar. X bar is the centroid point of this area. So this is the expression for the integrals. So we can use this expression to help us to evaluate the integrals in the virtual worker method. So how we can apply visual integration to do that. So as we know, using virtual work, the expression to calculate the beam deflection is delta equal to 0 to L small m. This is the internal bending moment in the virtual system. The internal bending moment in real systems, EI over EI times dx. So we can put EI outside of the integrals. So we will have EI 1. So from 0 to L is small m, capital M dx. So we know the m and the capital M is are functions of x. So it's similar to these integrals. And as we know, for the small m is the internal bending moment for the virtual systems. So the virtual systems is always a unit node. So we will see small m is always a linear function. So then we can apply this expression to help us to evaluate the virtual work method. So then we can apply this expression to evaluate the integrals in the virtual work method. So how to do that? So this will be, we put here, so this 0 to L small m capital M dx will equal to m x bar and A. So A is the area of the bending moment, so real internal bending moment. X bar is the magnitude of internal bending moment at x equal to x bar. So that's just to show how to understand this expression. So assume this is capital M. This is the internal bending moment in the real systems. This is the small m. So the A is the area of this bending moment diagram, and m x bar is the, if we see there is a centroid point C of this real bending moment. So this is centroid point. So if this is centroid point, then we can find, so related to this, we can find the value of this. This is mx bar. So because we know if we have a coordination systems, this is y, this is x, and the c have the coordinates of c is x bar, y bar. Okay, so then after we know the centroid point, the location of centroid point, then we know the x bar. After we know x bar, we can find the mx bar on this bending moment, reach of the virtual bending moment. So this is the expression for the visual integration. But usually we will have a table. So on every textbook of structural analysis, you will find a table. In this table, they provide the expression to calculate the integration, to calculate the integrals 0 to L, MQ, MP for the moment diagram from the virtual work method. So we can derive the expression by just using this expression. So we can derive it. So for example, here we have a bending moment. So if this is this one, and we have another bending moment. So this is M1, this is L. So because all these bending moments are linear functions, so M1, M3, M1 and M1 and M3. So we don't need to differentiate which one is small m, which one is capital M. Okay, because they are similar. So if we treat the M3 is, if we treat this shape is real bending moment, actually this shape is a virtual bending moment. So we will find is equal to mx bar times A. Okay, so A is the area of this. So what is A? So A equal to 1/2 M3L. So what is mx bar? So mx bar is the centroid point. So centroid point is C, x bar, y bar. Okay, so as we know, C x bar, so this location is 3L/3. So the location of the centroid of this triangle to the right hand side is L/3. So it's 1/3 of the L. So then we know if we can find the value over here, this is mx bar. So this is mx bar. So mx bar, so x bar is the location is L/3. So we can easily calculate the value over here is 2/3 M1, just based on the geometry information on these triangles. So then we have 2/3 M1. So after we know A, after we know the value of mx bar, so mx bar times A is equal to 2/3 M1 times 1/2 M3L. So it's equal to, we cancel this 2, is 1/3 M1 M3L. So this value we have derived is just for this expression. Okay, so this is visual integration for the virtual work method.